said, there's a couple people who are going to be presenting today from from the Interpreting Across Time channel. And so I'm going to start off by giving a bit of an overview of what we're up to and what we're hoping to accomplish. And then Igor has some preliminary results that he's going to present, and I have some preliminary results that I'm going to present. And then we're going to talk about kind of where we would like to end up for both the current phase of research as well as kind of our longer term plans, because this is something I hope to be working on for quite a while. So the origin of this project is that there is a lot of papers that in interpretability that study, like for example, the knowledge neurons paper, the example depth paper, that study interpretability concepts, and in particular, kind of like how and where information is represented or capacities are found within a neural network, but don't really look at that in the context of how the network changes during training. A really good example of the work that I want us to be doing is the AlphaFold paper, which I know there was a presentation on a couple of weeks ago, though I wasn't able to make that one, where they had these really wonderful plots that they called what, where, when plots. Actually, I should just pull these up to give an example. Sorry, I said AlphaFold. I meant to say AlphaZero.
That's right. Yep.
Acquisition of chess knowledge in AlphaZero. So let me share my screen briefly, so I can provide this as an example to people who don't know what I'm talking about, in case there are any. Here we go. Go live. Excellent. You can see my screen?
We can.
Yep.
So in the paper, acquisition of chess knowledge in AlphaZero is a study in how the AlphaZero chess engine develops its ability to play chess, and kind of at what stages of training different capabilities exist. So one of the cruxes of this paper are these plots that they call what, where, when plots. And so you have three axes here. One of them is these are classification. They are taking a part of the network, and they are testing whether or not it can determine whether a particular property holds. So, for example, here we have in check, has contested open file, can capture opponent's queen, has a mate threat. There's also ones that are slightly less categorical. So, for example, these ones are about the material imbalance, the numerical score that people assign to positions based on the fact that I've captured my opponent's rook and my opponent has captured two pawns in one knight, and the extent to which that is balanced or imbalanced as a set of traits. And so what you see, so these are all heat maps, and what you're seeing here is kind of three axes. So you have training steps. So 0 is the untrained network, and then 10 to the 6th is the number of steps that they've trained their networks for. Block is roughly synonymous, at least in the context of language models, comparable to the number of layers deep within a network. So you have a large network, and similar to some of the probing work, we look at kind of the first section or the first couple layers of the network, and we're interested in evaluating the accuracy. And kind of what they found is that they're able to map out in this pretty compelling fashion both at where in the network's depth certain abilities arise, as well as how much training you need to do to get them. And they do all sorts of analyses with these plots and correlations. And one of the things that I think is really interesting, for example, you can see in plot A, where they're measuring kind of the engine's ability to estimate the score, which is a proxy for how likely white is to win in a position. There's there's this really nice gradient that you see across training steps, where its ability to do this increases significantly and then plateaus. It after about they train for after about 10 to the fifth steps for the next 90% of the training. Its capabilities in this regard don't really go up, and so it's kind of plateaued, and you don't need more than that in order to get really good performance. Checking whether or not the engine knows it's in check, that arises even earlier. Performance kind of plateaus at like 10 to the fourth steps, despite the fact that they're doing 10 to the sixth steps of training. And then there are other examples. Here has a mate threat is slightly non-monotonic. And there's all sorts of interesting things you can say about these landscapes. This one is a complicated concept that the engine just never really develops very robustly. And so, I think that these plots are fabulous, and I wish that a lot of the interpretability research that people do with neural networks, and specifically with language models, looked more like this, because I think that this is really fabulous. And in the context of language models, I'm interested not only in how these patterns in language understanding arise across training, but also how the patterns across training change as you scale. So, for example, it is conceivable that, just to stick with the chess analogy, for example, it is conceivable that if you were to multiply the size of the neural network by 10, some of these, for example, in check, might not really change at all. You need a certain amount of exposure to data to develop the concept, and it's pretty easy to develop once you've seen the data. Whereas, as a proportion for how early in training, checking whether there's a mate threat arises could change dramatically. And as the neural network gets larger, it has more capacity, and it's able to develop this faster because in fewer steps as you scale up. And I think that doing that kind of an analysis would be really fascinating and really valuable to interpretability research. Unfortunately, nobody's really doing that for a couple different reasons, including the fact that there aren't good pre-trained sets of models to do this on. So big picture, what our project is about is studying this kind of phenomena, though more in the context of language. And what I want, that is not what I want. Sorry, I can't talk and think at the same time.
That's good. Take your time. Plenty of
time. And so we've identified, so we want to train a set of models that are consistently trained and consistently checkpointed, like what they did in, for example, the scaling laws papers, but release the trained models as well as all of the partially trained checkpoints, and kind of use these to power analyses of interpretability. I'm sure that they will be useful for things that aren't interpretability research as well, but kind of the big motivation from my point of view is one of the big motivations from my point of view is studying interpretability with it. Yes, so we have a couple experiments that we so there are two pieces to, I guess, phase one, I'll call it, of this project. One of them is to simply like train this suite of models that can be used to do these kinds of analyses. And then the other part of phase one is to put together a diverse and compelling set of experiments to show people, look at all the cool stuff that we can learn. And so we've gone and talked about a bunch of different kinds of experiments, and we've identified a couple that we are going to start off with. And Igor is running one of them, and he's gonna tell us about some of the preliminary results that he's found there. And then I've been doing some stuff with memorization, along with words. Sorry, I'm going to be doing some. I have been doing some stuff with memorization alongside ORs, and I am going to be presenting that after Igor talks about the really cool probing stuff that he's been doing. So I think that largely covers it. Igor, you want to take it away?
Sounds great.
For sure. Thanks, Stella. Can you hear me? Can everybody hear me and see my screen?
We can.
All right. That's great. I've talked to some of you on various channels and threads, but I'll just take 10 seconds to introduce myself. I'm from engineering product building background. I spent last 7 years at Pure Storage building a data storage product, and I'm currently collaborating with Sutter Hill Ventures at founding a next startup in AI, primarily with focus on B2B space. So I'm spending half of my time looking at the latest and greatest technologies in AI and really trying to have my hand on the pulse there, and the other half of my time looking at old crusty enterprise applications and trying to figure out how do we pair the two together and build an interesting company in that space. And so as a part of the AI research part, I've been spending some time with EleutherAI. I've really appreciated that I can drop in and if I'm can join projects and help out with things. I certainly appreciate you all having me here and tolerating my presence. Let me talk about some of the things that we've looked into as a part of the interpretability across time research track. So can folks still see my screen? I'm not quite used to this, or maybe I need to switch back. I'm not quite used to the setup, but I'll figure it out. So in the what, when, where plots, can folks still hear me?
Yep.
Okay. All right. Oh, I see. Okay. So in the what, when, where plots, one of the things that you need to be able to do is look across layers. So you need to be able to probe across depth.
Glass, mute yourself, please.
Sorry.
Oh, okay. That was what was confusing me. I was like, what's going on? So one of the things that you need in order to look at interpretability is to look across depth, like what's happening at different layers in the transformer. And the first, like the most basic question is, can we extract something out of a given layer in GPT-NeoX or any other language model? And so that's kind of the first question. And for those of you who have been following any of the interpretability discussion, you probably would have seen Logit Lens, or you would know that like dropping layers means that the model still continues to work. So this tells us that the prediction of the next token is present at lower layers of the transformer. And Nostalgibrize did a very nice, thorough examination of this concept, and we could easily spend an hour just talking about the Logit Lens. But in terms of what happens with the model, I kind of tried to illustrate it on the left side in terms of in terms of the components of GPT-NeoX, and I'll use this format on subsequent slides as well. So basically what we're looking at here is we just take the model and we only keep L layers, right? So we drop the top layers, and that gives us a next, that basically ends up producing a model that still works. It generates a next token prediction, and we can then, let's say, look at what's the perplexity on Wikitext, or what's the log loss on Wikitext. And so if you look on the graph that I'm showing here we're looking at perplexity on Wikitext as examined by Logit Lens. And we actually started at 0, so you can do Logit Lens prediction straight out of the input embedding. Interestingly, it depends whether if the embedding and unembedding are tied, like they're in GPT-2, it doesn't end up working because in that case, Logit Lens just ends up projecting back the input. But on GPT-NeoX, you can use Logit Lens to get the prediction out of every layer, which is that's super interesting. Now, the next interesting question is, Logit Lens shows us that the next token prediction is present in earlier layers. Now, one question is like, is Logit Lens the unembedding matrix, the optimal projection. So if we take the unembedding matrix, is it the optimal way to project the next token predictions out of earlier layers, or is there a better prediction? And if there is a better prediction, how much better is it? Is it a little bit better? Is it way better? So that was kind of the question that we started with. That was Stella guided me down this general path to go explore. And what the way, I mean, I've looked at this problem in a few different ways, and the way I approach this is to add an extra linear projection in front of the unembedding layer. So basically, instead of using the unembedding matrix to project the output of a given layer, we effectively fine-tune the unembedding. I've done this through a few different variants. I've done this by retraining the final linear matrix. I've done it by putting an extra linear transformation in front of the unembedding matrix and just fine-tuning that. And you end up getting the same thing in all the different variations. And so you get the second curve, the, I guess, orange dashed curve, that shows that actually you can get a much better prediction out of the residual stream compared to what you observe with Logit lens. And so this demonstrates that there is a much better prediction than what you might think from Logit lens. Now, I think the key part of the, I guess, thought process that I'll be going through is, okay, is the orange curve like overfitting in some way, or is it really demonstrating, to what extent it's really demonstrating knowledge that is present in that layer? Like, to what extent is it fair to look at the orange line and say that, hey, this is what the model knows at a particular layer? And so this will be something that we'll get to both from like empirical and theoretical side. But one thing that...
It's a quick question. Do you have any notion of the variability for each of those points? So like how much variance is around the blue points as opposed to the orange points?
Variability with respect to...
just the performance overall. So like how... Sure, the average performance is better for orange than blue, but is there just a lot of variability at different layers, or does the variability change, or
so
the things to look at in order to understand kind of the...
Yeah, so the orange line, can be obtained in various through various methodologies. I've tested this across various model sizes. I've tested it across various evaluation sets. So here I've trained the extra linear layer on Pile, and I'm evaluating on Wikitext. I've looked at evaluating it on Enron emails. I've looked at evaluating at other data sets, both that measure perplexity and also that measure other scores like Lambda and so forth. So the general results that I'm showing, I've validated by varying a number of different axes.
Yeah, I actually didn't mean that as a skeptical question. It's more trying to understand more just kind of what the distributions of those points look like, so that maybe, let's say that for 90% of the words you get a big difference in these things, but for 10% of the words, the performance is just as bad as, I don't know, random guessing or something for most layers. You could see different characters of different behaviors at different layers if you looked at variability.
Yeah. So the one thing that I'll have later on is I'll have an example, so we can look at a concrete example of what's a prediction that actually is generated by Logit lens versus the extra linear layer. So let's get to that, and then see if it's helpful, and we can take it from there. But so one point that I did want to make is, if you look at, the difference between Logit lens and the fine-tuned and the tuned lens is pretty huge. Like it's something like 8 layers in the most from like layer 0 to layer 8. And so sure, you have to believe that what the true knowledge of the model is, to the extent that such a thing exists, has to be much closer to the extra linear line compared to the Logit lens, because we've really only added one matrix that's like a million parameters, embedding space squared. So we've added relatively few parameters, and we got a prediction that's so much better. So even the most pessimistic interpretation, like you would have to imagine the true knowledge of the transformer is maybe like a quarter of the layer to the right of what the orange line shows. But it's certainly, I think it's certainly quite clear that the extralinear curve is a better representation of what a given layer knows about a particular prediction. And so we'll get to that point from different perspectives and angles.
One thing I want to pipe in at this point about is that there's a question as to whether or not tuning or changing up the methodology or doing some kind of fine tuning or doing some kind of prompting is cheating or not. And kind of the approach that we've had in general is that there is knowledge that is inside the neural network, and we're not necessarily trying to measure what exactly is going to happen if you query the network, so much as how much information or knowledge of what facts can we extract from the network in some way, which I think is pretty meaningfully important, because one of the main things that we're interested in with these networks is using them as a component in some kind of pipeline that is going to know a lot about about the world.
Yeah, and so absolutely. So like, to what extent are we cheating by drawing the orange line? I think that's the key question, and then I think that's like the main thing that the rest of my slides really come back to from various perspectives. So I think that's a very interesting question, and that's one that I'll get to from different perspectives. I also have here results from Lambada comparing Logit lens and extralinear fine-tuned projection. Again, you see the tuned projection doing substantially better, like quite a few layers earlier. I've looked at lots of different evaluation sets. One of the things that is nice about this methodology is you can apply any benchmark from, let's say, LM eval harness, and you can get the scores at any given layer. So that's pretty cool. Some of the benchmarks are noisier than others, and so sometimes it takes some time to understand it and interpret what's going on. So let's get to another question. Tuned lens, the way I interpret tuned lens is it's reading from the residual stream, or projecting from the residual stream into a prediction space. So what if we also tune all projections that write into the residual stream? And what I mean by that is all the linear projections that precede the residual addition. So let's look at kind of which parameters I'm talking about. So here, what I tried was I tried to tune the extralinear matrix, and then I also tuned attention dense and MLP, the output matrix of the multi-layer perceptron. So basically, we're tuning this is like 40% of parameters in each layer. And so now, question is, how is the curve going to look like? Is it going to be, how much better is it going to be than the tuned projection that we tuned on the reading from the residual stream? And the thing that was super interesting, and I would say, I think unexpected in a lot of ways, is actually tuning these parameters does not get you any benefit at all. So the way I'm interpreting that is the model already writes optimally into the residual stream. So all the matrices like the attention dense and MLP dense 4H to H, those are already optimally tuned. And as long as you know how to read from the residual stream, there's no extra benefit from tuning those matrices. And this is super interesting because now here I've tuned way more parameters than in the previous than with a tuned lens. With a tuned lens, I only tuned one square matrix in the embedding space. Here I tuned 40% of parameters in each layer, and there's no additional improvements. I think that's super interesting to think about this and try to incorporate that into the mental model of how the residual stream behaves. And so the next question is okay, what if we tune all the parameters? And I think that if I tuned all the parameters and I didn't get an improvement, then at least something went wrong with the methodology, because I think everybody expects that if you crop the model to a certain number of layers and then you retune it, you should get a better performance. So specifically with the tuned lens, we see roughly a linear behavior across layers. So the improvement in log loss is roughly linear across layers. And you would expect improvement that's behaves exponentially with respect to the layers. So I did this do this experiment where I retuned the entire cropped model, and we do get a curve kind of more along the lines of what you would expect. These are more finicky models to train, so you kind of need to use different learning rates for different sizes, and I didn't quite do enough hyperparameter optimization in the middle, so that's why the curve is not as nicely rounded as you would expect. It's a little buckled because I only use two different learning rates, one optimized for the left end, the other optimized for the right end. But you get this curve that represents how good can a model get in, let's say, 6 layers. And so you can look at how big can a model get in 6 layers versus if you have a 12-layer model, how good of a prediction can you get out of the sixth layer, which is a pretty interesting comparison. Does this make sense so far? Any questions at this point? We can look at other benchmarks or comparing these curves. I won't spend too much time on that part. And so I think there are 3.
I have one question actually, just on something you said a couple slides ago. It sounded like the model is already optimized for writing into residual streams, but humans want to read in an interpretable way, and it sounds like the model doesn't care about that part until maybe the very end. Is that what you're suggesting?
Right, exactly. So the model already writes optimally into the residual stream, but it's only, the prediction, the unembedding matrix is only optimized for interpreting the output of the final layer. And so I guess I'm making the case that if you want to read from the earlier layer, you need to read from the residual stream. I'm making the case that you tune this unembedding matrix for that layer, and that's the way you read from the residual stream. So that's sort of how I'm thinking about it.
Interesting. I think about. Go ahead.
I would also add that so when we're talking about tuning linear layers, kind of the question that you're asking is one of the inspirations for doing that, namely that a linear layer represents a change of basis. So if you think about each layer of the network outputting into a slightly different vector space, and so you have information that's being written into the residual stream, and as you go down the neural network, some of that information is getting modified or changed. But another significant portion of what's going on as you move deeper into the network is it's just changing how it's choosing to express that information. And so, but kind of the motivation behind specifically looking at tuning a linear layer at the end is that we are learning a mapping from the intermediate state that the model is in after 6 layers to hopefully a vector space that is more aligned with the embedding space. Sorry, an embedding space that is more aligned with the way the model is representing information at the end, and therefore, ideally, something that's going to be more compatible with like the unembedding layer.
Yeah, no, I think that's just really well explained. So if you believe that the embedding after every layer contains a subspace that has the next token prediction, and the subspaces can be different across layers, then it's a logical consequence that, like, okay, how do we read from the subspace? Well, we tune a linear projection to find that change of basis operation that's going to give us basically that prediction out of that particular layer. Because we've demonstrated that the basis is not the same across layers.
I think you could also turn that the other way, though, right? Because if you think of a linear model from embedded tokens alone, this is something that was brought up in the last circuit's work. That's basically modeling bigram statistics, right? You just go from the last token and give me a linear prediction of what the next token is. If I gave you the parameters of that model, it's not like you'd necessarily be saying that you're just reading out what the prediction was at the input, because I mean you get some information from those parameters, right? You're still, you learn something from from training those parameters. It's not like you're just reading out the embedding space at that point. So
Yeah.
there is some predictive extra stuff going into that as well.
So I think that is an important thought, and I do. I mean, I aim to address that in future slides, but absolutely. So linear transformation is not nothing, and you do have some parameters. Um, I guess I'll just make one comment here, but really address it much more thoroughly later, at least to the extent I have time, because I don't want to take too much time here. But even if the prediction was encoded in like specific bits of the embedding, like even if it was there, the model would still have to know to extract it from those bits, and so it would still have to do something. But I'll quite a bit more thoroughly in the next couple of slides. So let me talk through that, and then you tell me if it was helpful. All right, I mean, ultimately we end up with these 3 curves that I think are super interesting. You have the logic lens, the tuned lens, and then the retrained model curve, which is roughly logarithmic. And so we can look at a qualitative comparison between these different methodologies. I picked sort of an arbitrary prompt that was meant to test knowledge and grammar a little bit. So it says, at its peak, the Roman Empire. And I looked at layer 6 prediction out of a 12-layer model. Logit lens kind of generated something. So it said Roman Empire's largest known reality TV based off-duty. It's kind of like some phrases there, but not great. Tuned lens generates something substantially better. So at its peak, the Roman Empire was the most popular in the world, but this is the only thing we have seen. And then it kind of goes off the track a little bit. And then the fully retrained model is clearly the best one. And so qualitatively, you can see that it's consistent with Logit lens not doing so great, full retraining being best, and the tuned lens setting some sort of in the middle between the two.
Sorry, you say that the full retraining is the best qualitatively here because it still follows grammar? Like the content is still kind of strange for all of these, right?
The content isn't great, but now we are training a really tiny model here. We are training 6-layer model, which is that's really small. I mean, to me, at least the second one reads better. I guess it gets into a subjective judgment. I mean, the middle one kind of goes off track with it's a big eye up the other.
Yeah. I think at least I'm just trying to articulate what carries my qualitative impression, and I think it's just that the last one follows grammar while the other ones just kind of go into some kind of gobbledygook.
It follows grammar, but it also follows, like, it's talking about ruling, which is, it's tied to the concept of an empire. So, I mean, it's not giving you encyclopedic knowledge, but it's sort of saying things that reflect some understanding of the general topic, even though it's a pretty...
I would go as far as to say that for example, the Logit lens output looks a lot more like a sequence of somewhat randomly generated tokens.
Speakers.
Maybe you sampled from a giant text and you pulled out 6 tokens, you wrote them down, and then you sampled from the text again and you pulled out another 6 tokens and wrote them down. That's the kind of process that I would expect to give a sentence like what the Logit lens outputs. So
Do we know that JS.org and
I did not catch that question.
I think we have someone that should try to mute.
Well, Taylor, would you mind muting, please?
Hey, so I'll try to go through this in the next 5 or 10 minutes. So next experiment that I was curious about is Logit lens is effectively your projection, is effectively how unembedding matrix would perform on the earlier layers. So you can generalize this concept and look at how does a tuned lens on each layer perform on all the other layers. And so I did this experiment, and on the same small model, you can examine how do lenses trained on one layer perform across other layers. And so I don't necessarily have like a big fundamental takeaway from this observation, from this graph, but I think it's very interesting that you can see how the basically how the space changes across layers. So, and when you tune the lens on one layer, it does well on that layer. It maybe does okay on the layers next to it, but then it does progressively worse on layers that are further away.
Sorry, I'm having trouble parsing this plot. So the task itself is to not just train to the output, but to train to the representation to the other layers? I'm not...
Yeah. So let me talk through it one more time, or let me talk through it in more detail and hopefully more clearly.
That'd be great.
So previously, what I showed, and we can go back to this picture, the middle line that we're looking at here is for each layer, we tuned a lens for that particular layer. So like on the red line at layer 6, we've tuned a change of basis matrix effectively to transform from the output of the 6th layer into the output space. So we've tuned the lens to get the prediction out of the 6th layer. But now we're asking the question, okay, if I take this...
Quick interjection, he meant to say green, not red.
Yes.
I meant to say green, yeah, I meant to say green. The red line is irrelevant to, I guess, this particular part of the discussion.
Yep. Okay. I think I get it. So you're using the lens trained on, let's say, layer 6 throughout the network and seeing how it performs.
Yeah, on all the other layers, because that's exactly what I would argue the Logit lens is doing. Logit lens is taking the projection that was trained on layer 12, and we're applying it across all the layers.
Got it.
Right? And so I'm kind of generalizing from that. And so then you get this. So the pink line in this plot is the Logit lens, because pink line is the projection that was trained on the output of layer 12. And so it does best on layer 12. It does okay on layer 11, and then it does really poorly on early layers. So this is sort of an illustration of how the space changes across layers. This is the prediction space.
If I can provide a quick caption to this image, because I know there's a lot of lines and a lot going on. So in the key where it says like lens 5, that's referring to basically what's happening in the Logit lens, but instead of being tuned to the output layer, it's being tuned to the representations in layer 5.
Exactly.
And then, so that's the green curve. And so as the green curve goes through the plot, we're seeing what the performance is of that lens that's been tuned on layer 5 when it gets applied to the outputs of other layers. And the reason why these curves all hit the black line is because mathematically, tuning an extra linear layer is tuning an extra linear layer at layer 5, and then using it to interpret layer 5 outputs is the same thing that we're talking about. So
Yep,
it's like a mathematical tautology that unless something's deeply broken about your optimizer, it should be the case that all of these curves hit precisely the values on the black line. And so the kind of really interesting thing is the way that they bounce off of the black line, as well as the shape of the curve before it. So you can see kind of what happens when you misalign the interpretability lens with the residual, and how much that hurts performance.
Exactly. Yeah. Thank you for explaining that. You're absolutely right that the lines hit the black curve sort of by definition. I use the same run to get the ID because otherwise I have to just run the same thing twice. It really is tautologically the same thing as you said. But it is the interesting thing is how the colored lines bounce off from the black line, and perhaps the fact that you end up with something that looks like a line at the bounce points.
Something that I find really fascinating about this plot personally is that if you look at layer 12, they come out in the right order. So the worst is the one tuned for layer 0, then layer 1, then layer 2, and layers like 4 through 7 all get kind of close to each other, but they are actually coming, if you read them top to bottom, in terms of their performance, they are in order 0, 1, 2, 3, 4, 5, 6, 7, all the way down to 12. They're coming out in monotonic decreasing order, or to put that a little more clearly, if you tune a lens on layer K and then use it to interpret the output of layer 12, which is the last layer in this network because it's a 125 million parameter model, then the performance of that lens is monotonic decreasing in the distance between the layer that you tune to and the layer you're actually evaluating on. And that the fact that the difference there is what's determining performance is true almost everywhere in the plot. There's like a couple areas where it gets a little messy and the lines cross. But almost everywhere in the plot, the main thing that looks like it's determining the result is, or the loss in performance is the actual distance away in terms of counting layers that you are.
Yeah, that's super interesting. That's a really nice observation. And by the way, I would bet that some of the places where the lines cross are because I missed the run. So like in x equals 1, the green line is crossing. And now that I'm looking at it, I bet that I missed the point there. I didn't have a measurement. But leaving that aside, I think it's very close to very little line crossing given how many lines there are. We can look at a slightly larger model. This is a 24-layer model, and the same general behavior is follows. The lens trained on the input embedding behaves kind of a little differently from the previous model, from the smaller model. But I'm sure that will be interesting to try to figure out why it sort of drops down at the final layer, and how the final layer is a little bit more similar to the first layer than the layers in between. But it does show you basically how these output spaces out of the prediction in layer outputs changes in sort of this mostly gradual way, which is that's pretty interesting to me. And so I
one comment on the leveling off afterwards. I wonder if that's because the knowledge is simply retained in later layers. I would assume that if it were to forget the knowledge, then you'd see a decrease.
Yeah, so I think that when a line bounces off, there are two factors that are at play. One, like the later layers know more, but then the lens can't really take advantage of that, and the representation drifts. So the lens gets sort of less effective in later layers. So I think that's
Okay, it looks like
with.
Igor's internet.
Did you lose me?
Yeah,
Hopefully. Okay,
Yeah.
all right, I'm back here.
I think you're back.
So let me wrap up with a few thoughts, and I'll try to wrap this quickly so that we don't run over time too much. So I guess the first observation is that the next token prediction subspaces vary across layer, and they vary sort of gradually. And so we have basically output prediction encoded in the output of each layer, but exactly in which subspace it is seems to change gradually. Second thought is that we're using logit probing as a technique, meaning that we are generating logits out of a given layer, and this is something that enables us to run various language model tasks to evaluate performance at that layer, which is, it's not something I've seen in the literature. You guys know a lot of the research better than me, so but I think this is worth thinking about. And specifically, we recommend the tuned lens as the probing method. And now I get to I think the final thought, which gets back to the question from earlier. To what extent does the tuned lens reflect the true knowledge in a layer? And the argument that I am making is the way to think about the knowledge in a given layer is how accessible that knowledge is to future layers. Now, how do future layers access? Well, they always access knowledge through some kind of a linear transform. There's always a change of basis. You either have the KQV matrices, or you have the MLP pre-activation matrix that reads from the residual stream. The future layers always read from the residual stream by a linear transform. So they always access some subspace of the residual stream. And so the claim is that accessing any subspace of residual stream is something that's free to future layers of the transform. And so because of that, the claim is that that's why you can assume that the knowledge is known in that layer, because it's already encoded in a way that's effectively free for the future layers to access. And so I try to formalize that, and I guess apparently I didn't paste that correctly. So let me just fix that really quickly. Okay, this is what I wanted to show.
I should mention that it is nice to see a live person on video, but I think that might be hampering your connection a bit.
All right, let me turn it off.
It does seem a little smoother at this point, but let's see how it goes. Thank you for working with this.
Yeah, absolutely. So this is just my last slide, and I try to kind of formalize this statement. I kind of try to look at what I've seen empirically and try to look at it from the theoretical perspective. And so when you look at, so let's look at, for example, how keys are computed in an attention head. Well, you take the embedding from earlier layers, HI, and you multiply it by the key matrix for that attention head. And now let's say that we had a lens that was tuned at that layer. Well, then you can express the calculation of that. Then then let's look at the calculation of a key as an arbitrary linear transform of both hi and hi times the length. So basically we're saying like the key calculation accesses both the embedding and also the output of the tuned length. And basically just end up, when you go through the math, you end up just with a different key matrix. So you end up with a different key, matrix Kij, but it's still linear. Right? As long as the model learns the appropriate, it can attend both to the embedding and also it can attend to whatever the tuned lens transformation is. And so this to me is like a very interesting thing that the model does not need, future layers don't need any additional computational capacity in order to access this information that's in this subspace. The model still needs to dedicate a subspace of the keys to represent whatever information it's extracting out of the lens. But that's sort of a logically necessary requirement. Even if we were extracting the information out of the key vector through identity, or even if we were extracting the information out of the hidden latent state through identity, that information would still have to fit into the key vector. So to me, this is the argument that I would make, that the tuned lens represents information that the future layers can access for free. And so that's why I would say this is something that generalizes across transformers with NLP, computer vision, or whatever else you're using transformers for. So I'd be super interested to get people's thoughts on this, get feedback, and if you have ideas on how we can run experiments to either prove or disprove this way of thinking about things, I'm very interested to hear. What do you think?
Yeah, thank you so much for walking through this stuff. This is really great. Regarding this slide, I don't think I've necessarily parsed all the details yet, but I don't necessarily think that thinking of it as a change of basis as for free still makes sense to me. I think just the even the bigram model consideration that we were talking about before still kind of weighs on my mind, because it's not no information that's encoded in figuring out what you need in order to understand what the next token is.
So let me tell you, I've already kind of pointed out, let me just touch on that point. The way I would think about the bigram model is that basically bigrams are solvable, that the bigram knowledge can be integrated into whatever follows for free. Because after the way you read from residual stream is through a linear transform, and changing multiple linear transforms is a single linear transform. And so basically the bigram information can be encoded into whatever linear transform follows for free. And so that's how the argument follows.
I think I can see that part, but I think when you say for free, you mean a specific version of for free. Like, it's for free in the sense that it's free once you've actually done the training. But in order to figure out what the parameters are that you need in order to figure that out is still not no information anymore.
Right, and so that's
I think that there's two slightly different concepts going on here. When Igor says that the information is available for free, this is a different. This is not the same claim as saying that tuning the linear layer doesn't provide any additional capacity to the pre-trained model. Like we're talking about something slightly different here. What we're asking here is as the model trains, right? It gets so as the model trains in the lower layers, it has direct access to the inputs. It has like the attentions that come out of that, and it also has the intermediary computational results from the previous layers. And so one question we can ask is, as the model trains, does it need to do additional work to extract information that it has figured out in previous layers? If the answer is yes, that means that that could have a couple different consequences. One of which is that there may be some way to optimize the setup so that it doesn't need to do additional work to recompute things it's already figured out. But what Igor is showing here is that mathematically speaking, there does not seem to be. I mean, setting aside what it would mean to demonstrate this empirically, because I think that like nobody has demonstrated something like this empirically ever for any neural network. But mathematically speaking, there is no particular reason to think that as the neural network trains, layer 17 has to do any work to access information from the previous layers. Which is definitely not the same thing as saying that if we stick a linear layer at the end and tune it and use it to extract information, we're not adding information. It's a similarly structured but very very different claim. Does that answer what you're looking for?
That helps. I think I need to think about that more to parse the differences. But
Yeah.
yes.
So the main question in this slide is kind of how accessible is previously determined information to layers of the network? Because we've been talking this whole time about how they express things in different bases and how we have to tune additional parameters and add them into the network in order to get human readable outputs that make sense to interpret prior layers because the unembedding matrix is only tuned to the output of the last layer. And kind of the argument here is that even though we as humans have to do that in order to get information out of the previous layers, the neural network, mathematically speaking, is already doing that work when it's being trained. So that we shouldn't think that it is particularly cumbersome for layer 17 to consult the outputs from previous layers. And I think one reason why I think that it's important to think about this is that the way that like the circuits work, especially talks about the residual stream and writing into the residual stream, kind of assumes that there is this body of knowledge that you start off with, and then layer 1 modifies the body of knowledge, and then layer 2 modifies the body of knowledge, and then layer 3 modifies the body of knowledge. And if we make the claim that the input and output representation spaces are meaningfully different and that this makes them hard for us to actually get data out of when we move between layers, it suddenly calls into question whether or not you actually are writing into the same residual stream, or whether it makes sense to whether it makes sense to think about this as writing into the same residual stream, or perhaps writing into the residual stream in the same language. Because if layer 1 is writing with the layer 1 output embeddings and layer 17 is writing with the layer 17 output embeddings, we just showed you a plot that says that the layer 1 output embeddings, when applied to layer 18, do not give good results. And so there's a important question here of, is layer 18 actually able to read the stuff that layer 1 is outputting? And so that's kind of the context and stakes to this slide in particular, as well as kind of how it relates to what we were saying before.
Okay, I think that makes more sense.
Yeah, thank you. I'll wrap up here. Thanks for your attention. I'll be super interested. We'll share the slides, so if you want to kind of look at this stuff in more detail, it will be available. And I'll be super interested to hear what folks think, and if there are specific experiments or thought experiments that we could go through to either support or reject this way of framing the problem and thinking about it. Thank you. I'll hand it over back to Stella.
Great, thanks, Igor.
So, hello, can you guys hear me still?
Yep.
Cool. I got a pop saying the stream ended, and so I was just a little worried. So that was a lot of empirical results. Igor's been working on this for I guess 2 months or something like that now. that is most of the empirical results that we have. We're still trying to kind of figure out what we think the right way to interpret and think about these results are. But we also have a couple separate empirical results I kind of want to go over briefly that Ors and I came up with. This is actually stuff that we largely did prior to deciding to do this scaling model, but we weren't really sure what the best way to package it and present this to the world would be. And then once I said, we should start training this scaling suite and doing a bunch of interpretability experiments with it, it became a pretty natural place to present this information. So the thing that we've been looking at is memorization in neural networks. And something I observed just talking to people is that a lot of people, let me share my screen now. There we go. Yeah, so here's the punchline. The order of training doesn't affect whether or not a data point is memorized. So something I've observed talking to people is a lot of people have a kind of a mental model of the reason why memorization in language models and neural networks in general happens is something along the lines of the model starts off as the model trains, it has a body of knowledge or a set of representations that it has developed that explain things that have happened before. And some new information it encounters during training is readily explained by this, what's been developed so far. And other things it encounters during training are not. And if we want to get information theoretic about it, some new sentences that it encounters that are extremely different from sentences it has ever seen before require more bits to specify in an information theoretic sense, given the information that the model has been exposed to so far. And it can be a lot more efficient to simply memorize that information rather than do all of the work it takes to kind of rebuild the latent representation space to have a particularly to have a particularly efficient way to represent that information. And so kind of
like
one piece of empirical evidence. Oh, sorry.
It looks like looks like you're hitting the slideshow button has probably changed the window setting or something, but the stream has now closed.
Oh, wonderful. Yeah, I just wanted to make it bigger. Thank you.
That looks great. Thanks.
And so one piece of empirical evidence, this to be clear is not something that I'm claiming any particular researcher has published or something like that. But this seems to be a mental model that a lot of people have that I've observed just from talking to them. And before we started doing this was my mental model. But I think a lot of what we've done is kind of calls that into significant question. But there is good computational evidence of this. So, for example, if you go look at what content tends to get memorized, it tends to be stuff that, first of all, doesn't show up, that is structured extremely differently from stuff that shows up elsewhere in the model. So, for example, if you take a large quantity of internet text and you insert like a handful of 15-digit sequences of random numbers, those 15-digit sequences are much more likely to get memorized than some kind of baseline sample from your training data. And Carlini especially has done a lot of empirical experiments that have shown various things like this. And kind of the conclusion that I have reached from reading a bunch of his papers, and something that I know that he believes, because I've spoken to him about this a bunch, is that kind of the two big drivers of memorization, of determining whether or not a particular data point is memorized, is first of all, how frequently the model gets exposed to it. Because especially with these large language models, once you've seen it twice, you're already overfitting. And so as you increase the number of times you see the same string of text, when you're training a 6 or 10 or 20 billion parameter model, that has a really big influence on it because the model overvalues stuff it's seen before by a lot. And then the other one is just like, how different from everything else is the stuff that you are memorizing? And that's certainly not like the only factors. Exploratory analysis has shown that, for example, some book passages are memorized, and why does G2V2 have the first like 2 chapters of the second Harry Potter book memorized, but not the third Harry Potter book memorized? That doesn't make a whole lot of sense. And if you go and you look, they show up in there's definitely some other things, and possibly just like some random noise going on. But from the qualitative analysis that exists, it seems like a lot of the explanation of memorization boils down to those 2 things. First of all, exposure, and second of all, how difficult it is to predict a bit sequence. And so when we're thinking about how things change over training, the kind of natural assumption is that the order that data is presented in the process of training matters. If we have this picture of the way matters specifically to memorization, if we have a picture of the way that neural networks develop these kinds of representations that says it has a model of the world and it's incorporating data, and some of that data is easy to incorporate and other data isn't, but as it kind of goes on, it's continuously trying to optimize the representation that allows it to explain the data that's seen. Things that occur earlier in training are less likely to be memorized because they have had more time. They've spent more time sitting in the set of things the model is trying to optimize its representations for, and because the model has used that data as its prior to try to understand and represent other things it's seen. And kind of I guess I talked through the first several slides. Kind of the conclusion that we have reached through our experimentation is that this is just not true. Specifically, if you take a sequence of characters and you move it somewhere else in the training data, whether or not that sequence of characters gets memorized, like the probability of it getting memorized, does not change. So the way that we've gone about doing this experiment is we've taken we take the context and we split it into 2 groups. We take a document from the training data, and we say, okay, we're going to take the first n tokens. I think for these experiments, n equals 32, and we feed. So we take an actual training document and we take the first 32 characters, and we feed it into the model, and we ask it to predict the next 32 characters. And we're not actually interested in the top 1 predictions or something, but what we're interested in is the logits assigned to the true continuation. So you have a 64 character sequence, and when prompted with the first 32, how likely is the model what kind of probability does the model assign to the correct second half of that sequence? And blah 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 blah. Yes. So for a dense small model, there's a typo here. This is 125 million, not 150, but not really particularly important. So this is a bucketed histogram where the x-axis shows the index of the of the tokens in training, because documents have different lengths. The fact that these are token indices, not document indices, is important. And what you see, and so what this shows is a bucketed histogram. I think there are 20 buckets here, and this is the 75% range, as well as the lines between the medians. And if you look at the y-axis, this is a really small variation. We're going from negative 7.14 to negative 7.19 as the total variation across 3 times 10 to the 11 tokens in train. And indeed, if we look at the fit regression line for predicting negative log loss as a function of the token index, there's this y-intercept term, and the slope is 2 times 10 to the negative 15. That's about as strong of a statement as absolutely no correlation as you're ever going to see. And then we did it with a 350 million parameter model, and we saw the exact same thing. You'll notice that it has shifted downwards. We're now at like -9. Larger models tend to memorize less, which is another kind of implicit point in favor of the idea that representation capacity and having good representations is something that influences memorization. But the slope here is still 3 times 10 to the negative 14. And if we go up to a 750 million parameter model, we've dropped even further. We're now at negative 24, but we're still at 2 times 10 to the negative 14. And then you can see here's a plot of the regression line, so you can kind of see how they're spaced out. So first of all, it's fascinating to me that the difference between going from like 150 million parameters to 350 million parameters versus 350 million parameters to 750 million parameters is ginormous, because and actually goes in the opposite direction that scaling laws would tell you to predict. In general, scaling law says that if you plot things on a log-log plot, performance increases linearly with scale. This is not a log-log plot. However, I've done the math, and I can tell you that if we were to replot this on a log-log plot, the green line is closer. I mean, you can see this kind of numerically. Like the green line is closer to the blue line on a log-log plot than is the red line, in terms of the perimeter space. Sorry, I want to make sure I'm saying the right thing. I do, but I want to get more data points. And this was kind of one of the reasons why I said, okay, we should just train a lot of models. Because at the end of the day, this is 3 data points. And the hyperparameters for these models were not picked perfectly. And they were not picked incredibly consistently. So these were 3 pre-trained models that I had lying around because I was testing the GTB NeoX codebase. One thing that I really want to do, and one thing that's part of this idea of training a scaling suite that I think is really important, is using really precisely chosen values for all the hyperparameters and making sure that you are training on the exact same data in the exact same order, that you are that all of your parameters are scaling linearly on a log-log plot, that you are following kind of the scaling law's best practices, let's say.
How is the horizontality of these lines related to your claim that the order of training doesn't matter?
Okay, great question. So if earlier sequences are more likely to be, or less likely to be memorized exactly than later encountered sequences, we would expect to see that the negative log likelihood, that's a tough word to say, of latter sequences is larger. We would expect to see a positive correlation here.
But the x-axis is not the sequence index, but the token index.
Yes.
So the sequence index is entirely orthogonal to the token index.
Sorry, can you say that again?
The sequence index is entirely orthogonal to the token index, right? You have a bunch of files, and each of those files can be measured as a line. And now you're looking at how the performance varies as you go along the line, rather than as you go through the lines.
Oh, sorry, I thought I was muted.
No worries. So the question I have here that I think that this plot is a negative result for is it okay? We have the pile. It is 1.25 terabytes of text. It has been tokenized. It has been shuffled. We've decided that we're going to train for 1.25 epochs. Is what I believe these models have been trained for. Great. So we have 300 and we have 3 times 10 to the 11 tokens, and we're going to feed them in one by one autoregressively and start training on them. And the question is if you take a span of tokens that is in the first 10% of that 3 times 10 to the 11 set of tokens, and you take a span of tokens that is in the last 10% of that 3 times 10 to the 11 span of tokens.
I see. I'm sorry.
Is one of them more likely to be
Token
I
index
misinterpreted
to
this.
specify
I thought
like
this.
yeah, you got it.
Okay, I thought the token index, like I thought you projected the entire training set onto the relative position within a file. But what this is you have concatenated all the
That's right.
Yes,
files in the training set.
we're concatenating all the files.
Sorry
The
for
reason why, no worries. The reason why I was speaking earlier about the first however many tokens within a file. This is honestly a really good point of confusion because this is something I skimmed over that is intellectually important and can get confusing. The reason why we looked only at the first 64 tokens within any particular file is because files have wildly different lengths, and we wanted to make sure that the points that we were examining were statistically independent as best that we could. So if I have a very, very, very large file, so we didn't do literally every token because that would have taken forever. We did a lot of tokens. I don't know if Or's made these slides, not me. I don't know if he did not seem to have written down the number. I don't remember what it was off the top of my head. But we didn't look at literally every token. We took a sample, and what we want is that the samples are statistically independent in the sense that we would like to control for as much potential correlation between these tokens as we can. And one of probably the most important sources of correlation is that if you have a very large document and you train on all of it, but you sample multiple times. So you sample from, say, the first 64 tokens in this textbook, and then you sample from another set of 64 tokens that are like 100,000 tokens later in the textbook. The fact that they're coming from the same data source and show up consecutively can introduce a statistical bias into it, and it seems very plausible to me that the probability of memorizing a passage later in a text file is like probabilistically dependent upon the random variable that says, did I memorize earlier parts of this text? I don't have.
Sorry.
So
I was just gonna say that I don't have I don't have particularly strong evidence of this. It seemed like it was likely, and it seemed like the easiest way to control for this was to simply make sure that we were never sampling from the same document twice.
Every
there's a
30
lot of-
second sequence or every 30-second record of this was actually taken for training. I mean, evaluating.
Oh, this is every single sequence of tokens?
As in the pile, if you consider it to be a set of records, each having 2048 tokens, every 30-second record of it was taken for evaluation.
Not. Oh, okay. I thought. So tokens 1 through
As in
32
not
were
tokens,
taken.
actually sequences. It's records.
Yeah, I think the token sequence thing is maybe different, but you're just saying that files were, in some sense, sampled uniformly across the length of the documents, right?
Yes.
Yes,
Okay.
that is the moral of the story I'm trying to get to. Though I think I have mixed up some of the details. But that was the goal.
Was the training data shuffled before training?
The training data was shuffled before training and is in the same order for all three models. So it was shuffled once, and then each model was trained on it separately.
So one thing I looking at these numbers and looking how flat things are, I actually find I find this very, very hard to believe actually. How flat the numbers are, both in terms of like the scale and the and just the fact that we're seeing essentially almost no effect across time. I mean, you show it yourself with the regression line. It's basically, it's 10 to the, well, it's basically nothing.
2.25 times 10 to the negative 14 is actually stored as 0 in many contexts.
Yeah, I mean, to be fair, the token index is goes up to 3 to the power of 11, but I get what you're saying. It's a very it's almost completely insignificant. And again, I find this incredibly difficult to believe. One thing I'm curious about is how does the loss look like? Oh, actually, these are only up to 750 million parameters, I guess.
Yes.
And the data set we're dealing with is how big?
3.5 times 10 to the 11 tokens.
Right.
I'm sorry, I'm really bad at these conversions. I mean, this is like full GTP3 training data size.
It's the full pile. It's the full pile.
More than that, yes.
Huh. And we're saying the bigger numbers generalize. Well, the other thing I guess that's weird is the fact that the magnitudes here for the different models are different.
So the kind of base rate, the negative log
the base
loss
rate,
on
sorry.
average is different, though the extent of the variation is actually pretty similar. So here the extent of the variation is 0.05. Here it's 0.05. Here is 0.06. And you know that's definitely a very rough guesstimate. This is literally like matplotlib choosing what scale to use to fit to the image. But you know, 0.05, 0.05, 0.06 is the tick labels that matplotlib to put on these. So the variation within a particular model is not really changing very much as you scale, despite the fact that the actual overall value is changing dramatically. And so one consequence of that is that if you express this as a percentage, you know, what percentage of the negative log, I don't know particularly if percentages of negative log loss is a very meaningful thing to look at. Well, let's pretend for a second it is. If you're asking yourself, what is the percent variation in the negative log loss for dense small? Okay, and you ask yourself, okay, what's the percent variation for the large model? Those are like an order of magnitude different from each other. When expressed as percent change, despite the fact that the actual variation is staying the same, because this is more than doubling how far away it is.
Mm-hmm.
And
Oh, I was gonna say the negative log. So we're seeing the bigger. Just to double check again to make sure I understand what's going on here. We're seeing that the bigger models are actually doing worse. So they're assigning less probability mass to the previously seen strings than before. Is that correct?
The larger models are doing worse at the game of, given 32 tokens, predict what the next 32 tokens are in the training data. So in terms of kind of the capacities that we would like language models to have, I think most people would say that it's doing better. That we don't want it to be able to predict the next 32 tokens from the previous 32 tokens, because that would reflect too strong of a understanding of the distribution of the particular training text that's seen. Notably, this is not a skill humans have. If I was to show you 32 consecutive characters, you would not be able to tell me what the next if I write down 64 characters and I show you the first 32 of them, you are not going to be able to guess the next 32 characters in my sentence correctly. The overwhelming majority of the time. And that's because language just has a lot of variation. There are tons and tons and tons and tons of correct continuations, in the sense that like they form very reasonable syntactically and semantically valid sentences that I could have written down. In order for you to guess the next 32 tokens correctly, you need to get extremely lucky.
Sorry. So
or I need to be doing something trite. You know, if I'm quoting Shakespeare or something, you'll be pretty good at it. But in general,
what is the y-axis here? Just want to double check.
The negative log loss of.
Are you sure it's negative log? Because like it's negative.
Yeah.
Yeah, that was just the other thing I was gonna ask.
Yeah, so that would be, then it would be the other way around. then like then small would be like the best memorizing, which seems wrong.
No, that's what I'm saying. Yeah, that the small model is the best at memorizing. I think that is not unreasonable. I think that as the model gets larger, it develops more. Or so actually, let me rephrase that. It's not saying I'm not saying that the small model is the best at memorizing in the sense that like there are long passages, for example, that's memorized. I'm saying that the average extent to which it memorizes a particular sequence of tokens decreases. I do not know what the difference between those two sentences are. Like there's a very reasonable question as to whether or not those are the same thing or not. But yes, this is saying that the likelihood that the model assigns to the correct continuation is going down as the model gets larger, which is.
I just wanted to add that this is like the opposite of what I've seen with the OpenAI models, like comparing Babbage and Curie and Da Vinci. Like Da Vinci has memorized things to a much greater extent than the other models. So I wonder if this changes as the models become bigger, like maybe we're before the like double descent point or something. But I'm not sure. I'm really interested to see how this changes or how this looks as you do the scaling suite.
I'm just gonna say I'm just gonna say I'm confused. Actually, like this, I am not expecting the data that I'm looking at right now. If I'm interpreting it correctly, I'm not expecting it. Frankly, I would expect that the bigger models would be able to get better log likelihoods or assign higher probability mass to the target data, regardless of whether they memorized or not, because they should be able to leverage, patterns that they learned and stuff like that to assign higher probability mass to the next 32 tokens. So we should expect the bigger ones to be better.
So I've got one theory. I'm just going to try to interject. We talk about large language models as chameleons, that they're capable of being many people at once, many things at once. And maybe they are all memorizing, but in order to get the memorization, you need to prompt them. So a larger model is memorizing even more, but to figure that out takes work.
Yeah, that is definitely I think a very reasonable thing. These results are pretty solid in the sense that like we've replicated them on models of this scale. But I think that they're very preliminary if you want to draw conclusions about GTP3 or GTP Neo X or anything that's not like in this range of models. And I mean, I think we absolutely need to look at more models across more scales, that we need to make sure the hyperparameters are tuned to be as consistent as possible. And we need to do things like how many tokens of input prompting we're giving it and how many tokens of output prediction we're expecting it to have. So, hypothetically, it could be possible that a model is always able to get the next, like a specific model is always able to get the next 10 tokens, but is never able to get the next 20 tokens. That like it actually assigns a probability of 0 to the correct 20 token continuation, but it assigns a very high probability to the next 10 token continuation. And that is a axis of variation that we have not really experimented with at all. The best I can say is that this is definitely not tuned to give a negative result. We picked a thing that was primarily driven by computational limitations because this is very expensive. And we happen to get a very consistent negative result. But we should absolutely vary those things to make sure that we aren't accidentally cherry picking for a negative result.
I observed that these lines are so flat that you could have gotten at the flatness by doing a lot of less computation. you can, like, a simple way to reduce the amount of computation that you put into this is by taking only a random subset of the training data. Like, shoot out 9 out of every 10 of them at random. This should give you, like, already enough to say that the line will be flat, because then you know that the variation will be, like, smaller than 10 to the minus 10, where with the full amount you get that it's 10 to the minus 15 or something. Given that, I think it's given how absolutely flat this is, perhaps the effect is strong enough that you will still see it, perhaps even this strongly, if you do not do just the first 32 tokens, because, like, if, like, this is so lawful that presumably the law is simple, and we should find the simplest architecture where this still holds. For example, whether this still holds for MLPs rather than transformers even or something.
Yeah, that's related to a thought I have. I think a lot of the mental model that you talked to in the beginning probably comes from literature on catastrophic forgetting from way back before transformers. So it might just be a different regime or something.
Yeah,
Right,
that is fair. The overwhelming majority of results on, everything from catastrophic forgetting to memorization is not on transformers. There's like 6 papers, 5 of which were written by Nicholas Carlini, that are actually about transformers with more than 500 million parameters. So this is, in that sense, pretty unexplored in the particular context that I and I think most people in this call are deeply invested in.
Sure.
Would it be cheap in dev and compute to redo that small experiment with the entire training set?
I would have to do the math. I can say that we have been getting a lot of offers by people who think that EleutherAI is doing cool stuff, who want to give us compute, and that a lot of those people don't really understand what kinds of setups you need to train like a very large language model, that you need, high quality interconnect and stuff like that. But while, say, commercial cards are not very good for training large language models, if we can get access to a large number of commercial cards, there are definitely accessible ways to kind of massively parallelize this, and this is like 100% parallelizable. You don't need to do it in any particular. You don't need to do the analysis in any particular order. Once you have the trained models, you can literally run each inference on a separate card if you have that many cards. So I am very interested in kind of trying to figure out how to scale this analysis in different ways, and I do think that there is a way that we can make that cost effective, whether it's increasingly using subsampling, the way I think it was Gherkinglass who said that, or whether it's simply like, finding people who are willing to let us borrow like 2080 GPUs or other kinds of commercial cards that are a lot more accessible than A100s, but which, historically speaking, EleutherAI has not expressed a huge amount of interest in, because we can't use them to train large language models.
What probability do you predict that if you were to rerun this without the adjustment by looking only at the start of every file, you would get the same flat line?
High. I would bet 5-1 odds in favor. And that's like a literal offer if anyone wants to take me up on that. Like I would straight up, bet $100 on 5-1 odds on this.
I agree.
So, I guess one thing I want to take a look at. I don't know if we have the resources for it, or if it makes sense, or if it makes sense to take a look at. But I want to see, because this, from what I'm gathering, we're looking at the average memorization from like looking back throughout the training run. Is that roughly correct?
Yes, that is exactly what we're doing.
One thing I kind of want to see is I want to see the memorization of a single data point throughout the training run. So I want to see you have one sequence, and then about like say at the start or midway through the training run or whatever, the model sees the data point, and then we plot the log likelihood as a function of time, essentially, throughout the training process. Probably would be cool to do it like multiple time steps right after it sees it, and right before and right after, and then maybe like with increasing step size after that. But I think that would be something really cool to see if like how much does an individual data point actually move things. Because from what I'm looking at here, it seems like the suggested answer is it doesn't, but I somehow find that surprising.
So I think that's a really great question. I think I'm not 100% sure what you mean, mostly because I think there's a couple different ways to interpret what you're saying. One of them is we can say, okay, let's stratify this and let's go find the 10% most memorized data points in the entire data set. If we plot their locations, are their locations evenly distributed? So it's possible that the average memorization is constant, even if the location of the 1% most memorized tokens is not. And that's something that we have not yet done, and is something that I do want to do. Another thing is, some of these tokens show up multiple times in training, other ones don't. Well, actually, almost all of them show up multiple times in training. But some of them show up twice in training, and some of them show up 10 times in training. No, some of them show up once in training, and some of them show up 4 times in training. There we go. I know how this data was processed. I was definitely there and paying attention to what we were doing. So given the evidence that the number of times a data point is seen influences how the extent to which it's memorized, we can say, okay, what if we take the subset of the training data that's only seen twice and plot that, and then plot as a separate line only the data points that have been seen 3 times, and then plot as a separate line only the data points that have been seen 4 times. And what do those curves look like? And for this specific question, like, if you are interested in position within training, but you striate by number of times you see the data point, I don't know the answer. But if you are solely interested in like the extent to which seeing more data points influences the memorization, there's actually a really nice scaling curve for that. And there is a paper that I have seen a preprint of that is currently under review at some conference whose name I forget, but one of the ones with particularly stringent anonymity requirements. And so they weren't able to put a preprint of it online, but there is some really interesting results about like scaling laws for memorization, in the sense of how does the influence of how does the extent to which a data point is memorized get influenced by number of exposures. There we go. I think that was a coherent sentence.
Yeah, so I think what I was trying to get at is if you have like some unique, and you can, like you said, there's some things where it happens once, some things where it happens multiple times. But say you have just a unique string that shows up in the data set once. Just for the sake of simplicity, you can find maybe some that show up multiple times. But say you just had a unique string that shows up once in the data set. What I'm interested in essentially is how does the language model react, like as you snapshot the training at multiple different steps throughout it, how do those snapshots react to seeing the data point essentially? So I would expect something like... So
does it start off memorized and then become less memorized?
Yeah, exactly, right? So like what I would expect to see is I would expect a sort of a V-shaped profile where initially the model is learning to use generalization to figure out the thing that it's never seen before, which is the data point. And then when it does see it, I would expect to see something like a small drop in its in the loss, essentially corresponding to assigning more data to something it's seen before. And then after that, I would expect it to crawl back up as that gets progressively overwritten by more and more data that comes in. That is kind of my intuition for what I would expect to see.
So first of all, I agree 100% with your intuition. That is also my intuition for what we'd expect to see. There is a sense in which we are seeing part of that plot with the curves that I can show you right now, which is that we can see from the evaluation index of being all the way at the end of training, the various points along the curve for earlier data points. And I think that this implies this would be a lot more easy. It would be difficult to make consistent. What's the word for that? It would be difficult to simultaneously explain this and a very strong V shape in my mind. Like I don't think that those results are particularly consistent with each other. And so when we came across this, so when we came across
that's
this,
why I said I'm
deprioritized
confused about
doing
this.
that.
Yeah, that's why I said
I
like,
agree with you completely.
That my expectation is I would see something like that, and we're looking at something that says that's not at all what happens. So I think that is kind of the main thing that jumps out at me.
So I think it's when you think about a chameleon here, when a chameleon is not surprised, like a chameleon is both a Democrat and a Republican, and when the Republican sees something that surprises themselves, just give that information to the Democrat. Don't be surprised. So there might be a way that the chameleon nature of the LM explains this.
Sorry, could you unpack that?
There's not just one person.
It sounded more like a joke than.
Yeah,
I couldn't parse
that didn't really interpret for me.
You see some tokens that surprise you. There's not one person in the model. Somebody is not surprised by seeing that token, and if you are still surprised, you create another person. So. Who wouldn't be surprised? So, like, the capacity of the LM is a lot bigger than thinking that it's one entity that is either surprised or not surprised.
What you're trying to explain here is why the performance does not depend on the time it's been since the model has seen a piece of data.
So I think maybe to try to interpret the claim there, it's that language models don't have a single consistent, let's call it, point of view. If you generate from a language model many times, you will obtain extremely different continuations. If you ask it like a factual question, even you will, or especially with as you vary prompting and kind of as you vary the way that you're asking the question, you see very different types of answers, and sometimes you get the impression that the model knows the answer to a question. Sometimes you get the impression the model doesn't know the answer to the question. And so it's not like there's a person inside the language model answering things. It's a lot more like there's a crowd and that you are getting a random person from that crowd to answer the question each time you ask it. And so if that's how you're thinking about the way that language model generations come about, you might say, okay, so maybe some of these people living inside the language model that are producing the outputs have things have a particular fact memorized, and others don't. And that as you kind of do this and sample randomly from the model only once, and for negative log likelihood, there's a pretty large explicit average that we're computing over the probability of generation. Maybe the averaging across these different, I think, points of view is what David called it, cancel each other out. And so on net, there is no signal, even if there is some kind of more complicated thing going on under the hood.
You wouldn't
expect what you're getting at?
You wouldn't expect for a large mixture of models to have them all average out to exactly nothing like this. You would expect if all of them are like nothing and then one of them is something else, you would see that. And even if they're different, they wouldn't be exactly opposite to each other.
So one thing I'm curious about is like this is sort of like the very dumb sort of memorization where you just show it a bit sequence and it predicts the next 32 tokens. But is there like a more natural language sort of memorization where you can like ask it a factual question in natural language, and depending on where the text that explains the concept, even if it uses different tokens, shows up in the training data, does that change?
So yes, but I think that doing that properly is kind of dependent
really
upon
difficult.
the probing results that Igor, or first of all, yes, it is, whoever interjected that, is exceptionally difficult.
Me.
Being able to do it in an effective fashion is probably dependent upon very powerful probing results, like the ones that Igor is trying to find. I don't think that we have the capacity to do that experiment in a reasonable fashion today. Like, I just don't think that it's known how to do that.
Well,
I would have
so one possibility. Oh, sorry. Go ahead.
But I want to say, like, I feel like that's also extremely. It's gonna be, you're gonna see a large amount of variance down to prompting. It's all gonna come down to prompting, and so like how you prompt for the answer is gonna dramatically change how it matches what it's seen, and so I would not be surprised to see that this is just so noisy that it's not a really relevant result, or it's anything conclusive is what I should say.
Yeah, I was thinking maybe you could do something like putting fake facts at known points into the training data so that you sort of know what you're looking for, and then trying to fish them out with prompting. I guess the reason I'm sort of really strongly expecting this to work, or like to show difference across the training data, is sort of this picture of like learning how to learn that people have about GPT-3.
That would require for every additional fact you input to retrain the entire model, or perhaps like to retrain it once you've input all of those facts. But that brings me to like I would have expected that in order to check whether the training data order matters, you shuffle the training data and train the model on the new order as well, and then see if they agree. Do you think they would agree?
That is a great question, and that is an experiment I plan on doing. I have personally been kind of busy for the past month, training a different large language model. But no, I think that's a really reasonable question to ask, and I think that we should train a model and see if that happens.
I think it's a good idea.
We could then do like arbitrary inquiries into how they behave and then check whether they do the same thing, such as asking them about fuzzy facts that we really don't know when they learned them.
Yeah, I think that in terms of reasonably accessible follow-up experiments, the two things that I am personally most interested in doing next are shuffling the entire training data and rerunning everything, retraining the model, rerunning this computation, and seeing how much the results change. And then, well, hopefully the other one wasn't really interesting because I already forgot. I guess the other one wasn't really interesting because I've already forgotten what it is. There was definitely something else I wanted to mention as a particularly promising follow-up experiment, but I have absolutely no idea what I was thinking.
Also, I guess like this is kind of going back to Igoro's work, but one thing I'd kind of be interested in looking at is the Logit lenses that are being looked at. Has anyone kind of looked at, I guess, their dimensionality? Like, how sensitive are they to? How sensitive is the predicted token to movements in the parameter space in some directions versus others? and what's the ratio of those directions that matter to the predicted token versus the directions that don't matter, I guess.
So it sounds like you want to do PCA or TSM
Yeah, exactly.
on something.
Yeah.
What is that something you want to apply it to?
I guess it would be the residuals between the different layers. So wherever we're inserting the logit lens, essentially, one thing to look at would be, just for a simplification, assume that the lens is actually just a linear layer. What is the null space of that, or like the approximate null space of that linear layer, and what is its, the opposite of that, the space that is directly, that directly affects the output of that linear layer, and how big are those two with respect to one another? Or is there even that space? Like, what is the distribution of eigenvalues, so to speak, of the matrix, or maybe some approximation to it, that is being learned by the logit lens?
Yeah, so just a couple of quick thoughts on that. I did look at the tuned lenses. Can we interpret what the lens is doing? So if we tune a lens on the output of layer 6, can we in some way, can we look at it? I tried to visualize the matrix. I tried to look at the eigenvalues. I looked at it in various ways, but it wasn't trivially interpretable. Basically you saw some factor that had the most impact, and then there was sort of gradual long tail of of other factors, and so it seemed like the space is complicated, and you have to have the way I ended up interpreting it is there are various signals that you have to sort of subtract in order to get the prediction out, and so I wasn't able to get something that's trivially interpretable. So it wasn't like, oh, there's one eigenvalue that corresponds to the prediction of the next token or anything like that.
Did you share the matrix across the layers?
This is in the model where you train a matrix for the output of each layer. So there's a
Okay, so you don't share them. Have you considered trying to share it and then seeing how much the performance varies in that case? To see whether the dimensions, even if you cannot interpret them, mean the same thing across layers, if the performance doesn't really...
I did show the chart, right? So I did show the chart where you train a layer and how does it perform on all the other layers.
Oh, sorry, then I misunderstood that. Sorry.
Yeah, but that's exactly what the intent of that. Or how lens from one layer performs on the other layer, but at least able to kind of really trivially interpret what's in those transformations. Yeah.
Okay, I think this is a good time to at least call the official end of the presentations. Thanks so much, guys, for putting this stuff out there. This has been a lot of really good material, and I hope it's given people a lot to think about. I'm going to stop the recording here. But yeah, hopefully see you next time, and feel free to hang out for as long as you'd like.